Welcome everybody. My name is Christoph Fetzer, and in my presentation I will introduce an approach to ensure fail-stop execution in hostile environments. Most of you might already know about fail-stop execution, so that means that we execute a service or a program and we ensure that this is correctly executed. So whatever the program says, we faithfully follow the steps of the program. Or if we cannot guarantee the correct execution, we stop the execution before any wrong output happens. And we raise the bar a little in the sense that we consider hostile environments. That means environments where we have an adversary that has root access on the machine where we are running. So root access to the hypervisor, to the operating system, might be even an administrator of our application for which we want to ensure fail-stop execution. So we have some challenge here, and let's look into how we can solve that challenge. We are given a program that is written in an arbitrary programming language. It might use non-deterministic features like get time of day or having multiple threads that run in that process. That might use some mutexes to synchronize. So we are expecting there's some non-deterministic behavior with respect to the ordering of the outputs, and even the outputs might depend on the execution at hand, because it might depend on get time of day. And so what we want to make sure is that such a non-deterministic program is executed in a fail-stop manner. So either it produces an output that is computed in accordance to the program, or it stops execution before a wrong output is produced. So our program we could view as a non-deterministic state machine. And here on the slide we see on the right bottom some non-deterministic state machine. So it can get certain input, and it in some cases, say it's in state S1, if it gets input 0, it might go to S2, state S2, or it might go to S3. So it has some non-deterministic behavior. And what we want to make sure is that even in such a state machine that is non-deterministic, we can ensure fail-stop behavior. This also implies that we cannot just use replication, because one way of ensuring fail-stop behavior is that we have 2 or more replicas, and we compare their outputs and ensure that a majority at least of them agrees. And in this case, if we have non-determinism, there might be a disagreement even if all the state machines are properly executed. We can formalize an execution as a sequence of transitions. So here on this slide on the top right, we see the state machine. And in one correct execution, we might take the path from S1 to S2, then S4, S5, and maybe then we have to stay in S5. So this would be one correct execution. And for the same input, we might also see a correct execution that consists of the transition from S1 to S3, then from S3 to S3, and so on. So we have 2 correct executions since for the same inputs, because we have a non-deterministic state machine. And so that means if we have 2 replicas, one might take the first correct execution and the other one, the one on the bottom. So there might be a disagreement on the states that they reach, as well as on the outputs that they produce, these replicas. Sometimes there might also be a disagreement because the execution is wrong. So say we have an execution in which there is a transition from state S3 to state S5, which is not permitted in our state machine. But if that happens in the execution, then this is, of course, an incorrect execution. And what we want to do in a fail-stop execution is to make sure that this transition cannot happen. So before that transition happens, or could happen due to fault or some external influence, we want to stop the execution of our program. Actually, in reality, we might even be happy with a weaker assumption in which we just stop the program execution before it produces a wrong output. So we might permit the program to transition from S3 to S5 as long as there is no output. Or we might even permit a wrong output in case we can ensure that the output that is produced can be detected as being wrong by whoever receives that output. But here in this slide deck, I will focus on the first one. So fail stop execution. We stop the program execution before we have a wrong transition, actually, which means before we write a wrong content into the main memory. When enforcing fail stop execution, we have to consider the failure model that we assume and also the threat model. So in the failure model, we chosen the following. We permit single bit flips during the execution by a CPU, so there can be one bit flip, and we trust ECC. So we have memory with ECC protection. We can assume that bit flips in the memory are detected by the ECC. And so we have some previous work that actually underlines our work from Eurosys 2016. An alternative approach would be, our failure model could be that we allow more bit flips. We even allow CPU design faults. We might also allow memory bit flips. And we can handle this more general failure model by using what we call encoded processing. And there's one instance of encoded processing that we have investigated, which is delta encoding. So we have for each variable, we have two encoded values that should show the same actual value, but they are encoded in two different ways, and we can detect if they are wrong execution by comparing these two values before we output the value. Anyhow, so the slides that I present today, they will be focusing on single bit flips, but we know how to handle more or tougher failure models. Before looking at the threat model, let us first look at the application context. So what kind of applications are we interested in? So first, safety critical applications, like in the automotive domain. Maybe we have some software components that run, say, in a car, and we outsource that. So we started in an edge cloud to ensure that we don't consume too much energy in the car. We run that on some external edge infrastructure. And if we have such edge infrastructure, this computing might have, or the computers might have, limited physical security. So here you see a picture of a shipping container where they are computing inside. So it's actually a rendering, but these shipping containers exist with real CPUs and also GPUs that sit somewhere in the open with very, very limited physical security. So adversaries could actually try to access these computers, try to manipulate them, try to steal some data. And there might also be limited security with respect to IT attacks. So therefore, what we want to make sure is that despite using a shared infrastructure with limited protection, that we can ensure the safety and the security of our critical applications. So we want to make sure that the data is protected, the code is protected, and the secrets that we use to encrypt data and code are actually protected. Our threat model assumes that our adversary has already complete control over the infrastructure. So The adversary might have root access to the operating system, the hypervisor, to even our application maybe, and might be able to change the voltage of the CPU via some machine registers. So, and the reason for this assumption is that maybe we trust some cloud provider of the edge cloud that should not be trusted. And so therefore, our objective is that we can protect the data, code, and secrets of our critical applications despite the adversary having already complete control of the infrastructure. And so what could such an adversary do to our code? Well, the adversary could change that code, replace it by his or her own code, could change the configuration of our application, could change the data that is read from disk or that is read via the network. The adversary might even be able to change the hardware, the motherboard on which the CPU runs, or can change the system software that is booted or is modified during the runtime, this system software. So there could be also multiple instances of our services and applications started. The adversary might change the voltage of the CPU to cause some incorrect executions. So therefore, we have lots of attacks that we have to consider and still ensure that the execution of our critical application is fail-stop. So the first thing that we have to make sure is that the right code is executed. So we have to make sure that the adversary doesn't exchange our safety critical code by some different code. So this is the first step. Ensure the code is not changed. And then we have to make sure that our code is executed in the right environment. Say we want to execute that in an encrypted environment, so also called enclave, which I introduce in a sec. So we have to make sure that the code is there. And maybe we also have to ensure that the enclave is executed in a context of a certain operating system. So we have to ensure right environment. We have to make sure that the code is correctly executed, despite, say, undervolting that might cause some bit flips. And we have to make sure that the state that we stored on disk, so the state at rest, is correct. It has not been modified or rolled back to an old state. And also, all the requests that we process should come from a correct client. Of course, if the adversary could control the clients and send us requests to modify the state of the service, this might be also a cause of invalid executions, which could cause human lives. So therefore, we have to address all these issues. And there's one more thing. So we have to also make sure that an adversary cannot just clone the service. Because if we keep state, say, on disk, and the adversary can clone 2 versions or 3 or n version of our code, then of course the adversary could selectively drop some of the requests by sending that via the network to a clone of the service. So therefore, we have quite some challenges there. And let me zoom into one of the challenges, just as a reminder that if we have an application that typically the operating system, the hypervisor, does not trust the application. So it protects itself from the application. So it sandboxed this application. But on the opposite, application has to trust the operating system or the hypervisor, because if I do a system call in my application, the operating system accesses my memory in the application to, say, read something or to write something. The operating system needs access to the memory. So therefore, if I'm an adversary that controls the operating system, I can manipulate the memory of all the applications that run on top of that operating system. So that means in our threat model, where we assume that adversaries have root access that can change the operating system, in the traditional model, we lost in the sense that the adversary has complete control over our application. Therefore, we need a different approach. So what we use here is confidential computing. So we can protect the application from accesses from the operating system, the hypervisor, any other software, as well as hardware. So you cannot access the application via DMA. So what we need, of course, is some support by the CPU, and I get to that point in a sec. So in a summary, confidential computing allows us that only the application code can access the memory of the application. And what we want to achieve is that all the data, code, and secrets that our application has at rest, in flight, and in use is protected from all the other software. And that allows us to actually outsource the management of the operating system, the virtual machines, the hypervisor, even the hardware, to an external entity that is not part of our trusted computing base. We actually can even outsource the application itself, so the management of the application. And what we use for that is a concept that is called an enclave. So an enclave is a kind of a memory region in which I, as an application owner, can put in some code, some data, some secrets. And this is an encrypted part of the memory where only the code that runs inside of that enclave can actually see the code, the data, and the secrets in clear text. Everybody on the outside, all the software, hardware on the outside, either cannot access that piece of memory, that range of memory, or if there is access, can only see encrypted memory. So in this way, we can protect our code, data, and secrets in use. Typically, data at rest is protected by the operating system. And this is not possible anymore because we don't trust the operating system to do exactly what we want to do as an application, because this might be managed by an external entity that we don't trust. So therefore, what we do is we encrypt data that we store on disk inside of such an enclave, and when we read it, we decrypt it and check that it's properly decrypted and fresh, that data. And we have been developing a platform that is called Scone, that was published in OSDI 2016, that actually supports that transparently. So your application is actually not aware that it runs in such an enclave and that the data on disk are encrypted. Moreover, we can also encrypt the data in flight, so by transparently encrypting all the network traffic in case the application doesn't use TLS. One important part of the confidential computing is that we can establish trust, because we have to we have to put in some code inside of enclave, some data and some secrets. But actually, when we start an enclave, the adversary might see all that data and code that we put in there and might actually manipulate that code before the enclave starts. So therefore, we have to somehow establish trust in that enclaves. So therefore, we have to have some attestation. The attestation makes sure that the code that runs inside of that enclave is exactly the code that we want to run there. We can also ensure during attestation that the hardware is actually hardware that supports such enclaves, that it's up to date, has up-to-date firmware, has up-to-date hardware, and also that there are no open security advisory for that hardware that might affect the security of our application. Also, we have to make sure that all the clients that the application or service communicates with are also correctly started in a correct environment and the code was not changed. To do so, we need attestation. And so in a nutshell, attestation confirms that the initial state of an enclave, which is measured by the CPU and is a secure hash value of all the code and the data that is put in this enclave, is as expected. Also, during attestation, we can learn about some additional data item, typically a public key or a hash of a public key that the enclave during startup has created. So during startup, an enclave creates a random public-private key pair, and the public key is part of the attestation, which we call a report, which includes the Mr. Enclave, so the hash value of the initial state of the enclave plus a public key. This is signed by the CPU. And then what we do in the context of Scone, we have a configuration attestation service, which is called CAS, that checks that report, checks that this comes from is signed, the report is signed by an up-to-date CPU, genuine Intel CPU, and no security advisories. And then it checks in the policy certain other factors that need to be attested. And after that, it releases secrets to the enclave. And these secrets contain, for example, keys for the file system, arguments for that application, environment variables, files that are injected in the file system that might contain configuration files, and the configuration files might contain other keys and secrets. So in this way, we can configure the enclave with secrets and files and ensure that this initial configuration cannot be modified by an adversary. So far, we looked at making sure that the right code is executed in the right environment, so up-to-date trusted execution environment. We can actually also make sure that it's in a right operating system environment, so the operating system was booted properly. All the programs that were started in the operating system were properly checked. And now the next step is to make sure that an adversary cannot change the program execution by, say, undervolting the CPU to cause some wrong execution. So we have looked at that. So Artie, one of my PhD students, has looked at that with a system called Profi, which was published in SRDS this year. And this is based on some older work by a previous PhD student, Dimitri, which was published in Eurosys 2016. And there we looked at a system that transforms programs using LLVM to add instruction level redundancy, or also transactions that recover after we detect a bit flip. And the idea of instruction level redundancy is as follows. All the operations are actually executed twice. So here you see add, where you add x plus y and assign it to z. And here we just add 2 times x and y. So we have 2 copies and in two registers. So there's x and x2, a y and y2, and then the result is in z and z2, and we compare the results. And if they are not equal, then we go and crash the program. So we do a fail stop. And this is instruction level redundancy, ILR. And in the case of halved, we can add some tolerance and abort or execute the operations in a transaction and abort if there is a miscomparison, and then we retry. And the process of building applications is as follows. We have to first transform the code, say it's C code, using a C-lang compiler or LLVM, and build the code to include the instruction level redundancy and optionally the transactions for recovery. Then we also need to use the Scone cross compiler to ensure that we can run inside of enclaves, because inside of enclaves you cannot execute system calls. So you have to modify the way system calls are done. And one way to do that are cross compilers. We have also in Scone now a binary translation to do so. But since we anyhow use a cross compiler here, it makes sense to also use the Scone cross compiler to combine the safety protection and security protection. And so then we combine these two and get a binary that is protected against bit flips, as well as having all the facilities to run inside of enclaves. Now the question is, how should we evaluate this system? In here, we actually use an approach that was published in the literature, which is plundervault. So undervaulting the CPU to cause real bit flips, not doing some artificial fault injection, but using undervaulting to evaluate the system. And for that, we have a simple program to test. So we have a multiplication of two values. We check if the result is the expected result, and then we continue in the while loop. Otherwise, we exit with an error code. And for the evaluation, we have timeouts. So we stop the loop after 35 seconds or 100 seconds, and then we iterate for 100 times or 1,000 times then. And what we see, if we iterate 100 times, in 100% of the cases, we exit with an error in native code. And if we have 1,000 iterations, we sometimes see some iterations where there are no bit flips detected, or the result was always correct. Then we run that in the enclave, and there we have slightly better values. So in case of 100 iterations, between 93 and 99% of the tests were wrong results detected, but there were some tests, more tests, where we didn't detect anything. Okay, so then Profi, without recovery, so only instruction level redundancy, we actually see very little, nothing. That means without recovery. So 0% of the results were wrong. So by having instruction level redundancy, we actually can detect all the faults that we got through undervaulting. If we do recovery, there we see that we have some wrong results. So recovery actually reduces the correctness a little. And therefore, if we really want to have fail-stop behavior, we don't want to have recovery Profi without recovery. So just instruction level redundancy seems to be the better approach. If we look at the overhead, there we can see that the recovery actually costs us in overhead. So we have here some benchmark programs, and there we see that just by running in the enclave, the overhead is not that high. By having transactions, we actually we get some more overhead, and if we have Scone plus transactions, so Profi plus recovery, then we have even higher overhead. But if we have just Scone plus ILR, so no recovery, then actually overhead gets a little lower. So these are benchmarks, so you see different performance there. If you look now at some more interactive application like a HTTP server, and there we see, and hopefully you see that in these smaller graphs, that if we have a HTTP server in C, there is no difference between the alternatives. So we get about 20,000 transactions a second, independent which variant we are running. If you have actually a Rust version, there you see the orange one is native execution, and then there is Profi and Scone only. They have the next best execution, and then if you have half service recovery, then the performance goes further down. If you now look at, instead of Rust, we look at Python, then actually the Scone variants are faster. So Scone and Profi. So we have slightly different execution using Scone when we have Python, and there in this example there we have better performance. But if you look at the throughput of Python versus the C, of course there's an order of magnitude difference there. So therefore it's not that unreasonable that we might have a little better performance sometimes. Okay. Now let's look at another problem, this cloning of clients and services. And what we have looked regarding cloning are trusted leases. So there we have a paper, one of my PhD students has a paper in SOX last year. And there the idea is that we require that the enclave has a trusted lease before it can continue running. So kind of it has to stop if the lease expires. And let me try to explain that problem. Say we have some consensus like Raft. There in Raft consensus we have epochs where we have a leader, and say we have 3 different replicas in this case. And each epoch we have one leader. And now if an adversary might clone our replicas, what could happen? So we might have here the 2 clones on the top and the bottom. We have clones of each replica. So there's replica 1 and replica 1 prime, 2 and 2 prime, and 3 and 3 prime. And say the adversary also does a network partition so that the blue replicas and the pinkish replicas cannot talk to each other. So that means we might have 2 different leaders in the same epoch, and that means that Raft would be able to decide different values in the different clones. And then the first kind of replicas versus the clone replicas, they might decide different things. And so the idea to solve that cloning is that we have leases, so we have a trusted lease service, and at any point in time only one of the 2 replicas, so replica 1 or replica 1 prime, can get the lease. So therefore only one can survive. So as soon as a replica's lease expires, it has to crash. So in this way, one could use leases to solve that cloning problem. And we have done that with the help of these trusted leases. So in this case, when we have trusted leases, we can make sure that only one of them can get lease. And say in this case, we have replica 1 and 2 having a lease, and replica 3 prime has gotten the lease. And since we have a partitioned network, replica 1 and 2, they don't talk to replica 3, 1. And so in this case, the blue replicas actually can continue and take their decisions. But maybe an adversary learns about this and does the following. It first ensures that replica 1 and 2 get the lease. So in the blue replicas, they elect a leader and decide on something. So in Raft, you have a decision log. So say there's a proposal of deciding A, and these 2 replicas decide on A. And then in the next epoch, the adversary steers the network in such a way that replica 1 prime and 3 prime get their lease. Replica 1 will crash because its lease has expired, but replica 1 prime goes up and 3 prime goes up, and the adversary might have partitioned the network and the disk so that replica 1 comes up and sees, okay, I'm the leader in epoch 1, so there is a proposal B, so I decide on B. So that in this case, we would have in the two partitions, in the clone and the non-clone partition, we have two different decisions, A and B. So to solve this, we have to make sure that the state at rest is correct. So let's summarize that problem again. So we have here the blue and the pink replicas, and they should be in different states. So when replica 1 prime continues, it should see that replica 1 actually decided already on A. So the log has to be visible to replica 1 prime when it starts, when it gets the lease. So therefore, what we do in Scone is to make sure that the state that a service reads is integrity protected, confidentiality protected, and consistent. So it gets the latest state that was written on disk. So we have one could call that a rollback protection, this consistency requirement. So we rollback protect this persistent state. And in this way, when replica 1 prime starts up and it sees the old state, it cannot continue because attestation will fail. So in other words, we also solve the problem of protecting the state at rest using Scone, and rollback protection is actually enforced by Scone CAS, our configuration attestation service. So one last point that I want to address in this talk is how can we make sure that the client is correct? So what we actually support is a mutual TLS-based attestation. So we can make sure that our peers are actually satisfying their security policy. So all services are associated with a security policy that is maintained by the Scone CAS. And what we can make sure that if two services want to communicate with each other, that they can only do so if they both satisfy their security policy, and that they got the right client and service certificates to be permitted to talk to each other. So we have actually something that we call a network shield, and that network shield requires certificates, and these certificates and private keys associated with the certificates can only be emitted to a service, here in this case service A and B, in case they satisfy the attestation policy. So a little bit more concretely, when a service starts up, it gets attested and it gets certificates. Here, like a client certificate together with a private key that is signed by a certain CA certificate, and we can guide or we can generate dynamically these certificates with the help of policies, and in this way we can make sure that services can only talk to each other when they have the right, satisfy their policy and are part of the same application. So the attestation is guided by policies. Here is a very simple one on the slide. So each service is described what kind of, how it's attested. Like one can specify the Mr. Enclave, so the hash value of the initial state of the enclave. One can actually specify a few more things that are beyond this talk, and we can define certain secrets that should be emitted to that service after a successful attestation. Okay, so what are the next steps? We are currently ensuring that this lease service and the Scone CAS, there's also only a single instance. So if you seen or listened, I actually didn't explain how you can make sure that the strong cache, and also the least service, there's only a single instance because you need that too. And you actually need also fault tolerance. So this is some ongoing work. We have also some real-life use case with which we want to evaluate this system. But of course, there are lots of open questions that you could focus on in case you're interested in this topic. So one example is, how does it compare with bits on time fault tolerance? And bits on time fault tolerance, we need to assume that there is a maximum number of faulty entities. Here in this context, all the computers might be having problems. They might all have adversary on them. So we might not need that F, but we have different assumptions there. Like that our attestation is correct, that we can trust it. Also, we might not only want to have load time attestation, but also runtime attestation. So how could we support that? How can we make sure that this is portable across multiple clouds and CPUs? How can we improve the ease of use? And how could we support different protection levels? So there are lots of open issues that would be interesting to address. If you have any questions, I would be very happy if you would ask them and we can discuss about them. Thank you very much.